Hello, hope you can see me. I don't know what that background is. I don't remember setting this up, but who cares right now? I don't even know how to remove it actually. Weird. Anyway, welcome to Munich.net meetup. Sorry for this weird intro, but anyway, I was also surprised with this here. Hope you can see me. I am George, and together we're gonna go through the first steps of the quantum world. It's actually, of course, not anything production ready, but it would be, I guess, playground. It is for me. It was very interesting for me. So, um, first of all, I just wanted to mention that I am recording this session. I plan to publish it to YouTube. So if any one of you disagrees, if you don't want to be there, or I don't know, if you think that you are shared somehow and you disagree with that, please reach out and we will fix things, right? So today, quantum basics. What we're going to see, we're going to see some quantum physics basic things about superposition and entanglement. We're going to focus more on the superposition because that's what we're going to do today. We don't have time for everything. And after the theory, we're going to see some actual code on how to play around with QSharp in your computer using Visual Studio. So this is me. I'm George. I'm a software architect at Tech Cycle Solutions, and I'm organizer of Munich.NET Meetup and Munich TypeScript Meetup. And for everyone that wants to reach out somehow, either from that previous topic that we were seeing before. So, for example, disagreeing with recording this video, you can use my Twitter account, which is highlighted there, or of course any of the other ends through the meetup.com platform. Now, let's slowly start. Give me a second because this thing is very annoying and I have no idea if you actually see me talking right now. That wonderful, nevertheless, background, but I don't know how I did it. Yeah, anyway, I shouldn't care, I think, so much. Anyway, so let's start. There are some problems so difficult, so incredibly vast that even if every supercomputer in the world worked on the problem, we would still take longer than the lifetime of the universe to solve the issue. So this kind of phrase represents what exactly the problem of regular computers are today. They have some limitations, right? They have some limitations that we face in our everyday lives. Numerous problems in environment, in health, in agriculture, and in many other fields have a solution actually, but that solution is lost in a vast ocean of possible answers which need to be tested one by one for correctness. That is actually our today's problem, and thus enters quantum computing, right? Now, what's quantum computing? Quantum computing is the use of quantum mechanical phenomena such as superposition and entanglement to perform computations. Now, before I go further with this, I would like to show you something very interesting. This is actually IBM's new 53-qubit quantum computer, right? And this, I think the quantum computers are in these, oh, where is my mouse? In these cylinders in the middle. Now, what do we see though here? This is ENIAC. This is the first electronic computer used for general purposes, such as solving numerical problems. And what's the common here? There are actually people inside the computer. The computer is an entire room. And nowadays, we have a vastly more capable processor, more than one actually, in only our cell phones, right? So from that image here, we went to our cell phones. And from that image here, we expect at some point, sorry, it's one bug, at some point to go to something marvelous. I don't know if our children will see it. I don't know if we will see it, but the future seems exciting. So let me go back to our computing, just basic theory. So as we've seen already, quantum computing is the use of quantum mechanical phenomena such as superposition and entanglement, right? We use these quantum mechanical phenomena to perform computations. Now, these quantum mechanical phenomena are described by quantum physics as the behavior of atoms and other fundamental particles, like, for example, electrons or photons. A quantum computer operates by controlling the behavior actually of these particles, right? But in a way that is completely different than what we know today, than from regular computers. Quantum computers are vastly more capable of solving problems like integer factorization, for example, which underlies RSA encryption, right? So, but unfortunately for now, they are notoriously difficult to build and program because they are crippled by errors to such a degree that their operation falls apart completely before any non-trivial program has any chance to complete. I'll just stay a moment here. We said that integer factorization, most of you know it already, underlies RSA encryption. RSA encryption is based on the practical difficulty of factoring prime numbers, right, by using classical algorithms. Quantum cryptography, though, promises information security by harnessing basic physics rather than complexity assumptions. RSA is only safe today because scalable quantum computers are not yet available. But after quantum computers are available and built at large scale, polynomial time quantum algorithms might attack the underlying math problems for these crypto systems. RSA would not, unfortunately for all of us, be safe anymore. So you can imagine for what power that is for the first country that actually has a working quantum computer, right? It makes me wonder if the first one that actually succeeds will like give it to us, give it to the rest people, to the rest of the world. Nevertheless, what we know so far is that Microsoft, in cooperation with the Microsoft computer researchers, they are developing estimates. The thing is that for now we only can have estimates that how easy it would be to break current encryption systems. And they are also working on systems on how to make those systems robust again against quantum attacks. What has been proposed is the development of post-quantum crypto systems, and that is actually classical protocols that are resistant to quantum attacks, right? So there is a lot of research here and a lot of things that are going on, and it's in a very early stage, but in a very exciting stage because it shows how exciting our world will be, and you will understand that when we start discussing about superposition, which is actually now. So I remove that log over there. You actually see it in that bad quality GIF over there. What is superposition, right? Imagine or see those two colliding waves in the sea. Sometimes, like probably this bad quality GIF, they perfectly add to make a bigger wave. Sometimes they completely cancel each other, but more usually it's something in between. This constructive or destructive interference of waves is also called as superposition, and it actually exists. Yeah, you can see that in classical physics. Sorry. So you can also see on the left a very simplified diagram. A, constructive behavior of two completely aligned waves, they produce a much bigger one. B, destructive behavior of two aligned waves, but oppositely aligned, it ends up with nothing. And something in between the C, where this is more usually what happens, you end up with a new wave. So in quantum mechanics, superposition, we have superposition there, but it's a bit weirder, and actually, I think much more weirder than that. Particles that exist in different states, for example, in different positions or moving in different speeds, accelerating, decelerating, spinning, are thought of as existing across all these possible states at the same time. So they are both at two positions at the same time. They both accelerate and decelerate at the same time. It's very weird, but yes, a particle in superposition can exist in two places at the same time, or, for example, move at different speeds simultaneously. This, for us, unnatural. Since it is nature, it's not unnatural, but for us, a natural state of matter, practically, I think practically impossible for a human brain to comprehend. It's one of the weirdest realities of quantum physics. However, this weird behavior becomes human-friendly, human-readable, once a measurement of that particle is made. When, for example, we check its position, no matter how we check it, the superposition is lost, and it's not anymore in two positions at the same time. It only exists in one. This is a very weird. Oh, when I first read it, I thought, what's going on here? How can a particle know when I see it? How can a particle know when I observe it and suddenly change state and existing only one? Well, it's relatively easier, less weird actually than this weird superposition state. Of course, if light hits up my phone, my mouse, nothing will happen. It might get a bit warmer, but nothing will happen. But for the particles, for this super small world, if a light wave hits that particle, then it affects it. It makes it, it forces it into changing state. And how can we monitor, how can we observe something if not by sending some sort of, let's say, light wave into that particle and read back the response? That only by that. This is why by observing it, we are changing its state. So there is a famous thought experiment by the Schrodinger's cat, right? If you don't remember that, it was it's saying that we place a cat in a box, in a sealed box, and a mechanism in there that has exactly 50-50% possibilities of either releasing a gas or poison gas or not. What will happen after the theoretical choice of this 50-50 mechanism? Will the cat be dead or alive? Will it be both? Actually, this is a thought experiment. It never happened, of course, in real, because we know what would happen. And it was an attempt to illustrate the problems of a Copenhagen interpretation, which was an attempt of trying to apply quantum mechanics into our everyday objects, right? This was an early attempt in 1926 again. It was an attempt to unify this weird behavior, saying that, maybe everything until we observe, until someone observes it, has a unnatural state. It's not the case, of course. So yeah, I think we can go one step ahead. Now, what is qubit and why does it somehow matches with this superposition? Well, a qubit or a quantum bit is the quantum mechanical analog of a classical bit, right? In classical computing, the information is encoded in bits, where each bit can have the value 0 or 1, nothing else. In quantum computing, though, the information is encoded in qubits. Yeah, right. A qubit is a two-level quantum system where the two basis qubit states are usually written as 0 and 1. Actually, 1, if you see the south pole of that sphere, and 0 for the North Pole. This pipe 0 and bigger than is the way we are writing the state of a qubit. It's called ket. We will see that a bit later, but anyway, it's yeah. This mostly illustrates that a bit has two states, 0 or 1, but a qubit has everything in between, not just 0 or 1. So this sphere is called the Bloch sphere, and it's a geometrical representation of the pure state space of the two-level quantum mechanical system. So yeah, if we see that graph more or less, it maybe illustrates it a bit better. What we have here is a ket. This is the 1 and 0, and we have the kets here named up and down in this position, or this not very descriptive name that they have there. And they are showing that this proton is by 64% or 0.8 closer to 1 and 6 closer to 0, or the opposite anyway. So yeah, since an electron spin, that thing has only two possible states, up and down, we can associate those individual states with either that weird, let me enable, give me a second to get some paint here, with either, can I paint on a GIF? I don't even know, to be honest. I can, it seems. So this thing here is actually the up, which symbolizes 0, and this down here, if I can find my marker again, I can, yeah, it symbolizes the 1. So sorry for that breaks, but yeah, I need to confess something. Yesterday I had a terrible toothache, and I went to the dentist, and yeah, I had to remove the teeth, and I'm now with painkillers. So from time to time, I just need these breaks in order to reduce the pain a bit. Anyway, that mostly represents, let's go forward, and let's talk a bit about entanglement. This is another thing that is very interesting for quantum computing and for quantum physics, because it underlies somehow teleportation. We're not going to see much about entanglement today, but it's actually a very, very interesting topic. And there are numerous examples out there that you can write Q# to implement some sort of teleportation. So what is that? Quantum entanglement, and let me remove that thing over here. Quantum entanglement, Einstein described it, first of all, as spooky action over distance. What that is a relationship between fundamental particle properties that persist over distance without requiring transmission of information. So when we have two particles entangled, and one particle is, I don't know, in the other end of the world, in the other end of the universe, wherever it is, then the properties of those particles are bound together, and whatever change happens to one, then instantly it happens to other without transmitting any information of now change from spinning up to down, for example. So you can imagine this is actually an image, a GIF by James O'Brien. He made it for Quantum magazine, and sort of describes a very usual example for entanglement. Imagine that we put each member of a pair of gloves in boxes, somehow without seeing them, and mail one of them to the opposite side of the earth, right? Whoever is the recipient of should be able, by looking inside her or his box, to determine the properties of the glove that we still have with us in our box. That more or less makes sense in our world. Of course, if it was initially a pair of gloves and I sent you one, you will know if it's red or blue, what I have. But imagine, for example, that this recipient, the one that got the other glove, suddenly throws that gloves in green paint. Would that make your glove green? Yes, in the quantum world, it will make it green. If it cuts it in half, it will cut in half. If it moves it up or down, if it spins it, whatever it does with that, it will instantly happen to our globe here. This is another very weird behavior of the quantum world, which is, yeah, a very good idea to have as a basis for maybe future teleportation, at least for future for teleportation of information, right? No more lagging or internet speed questions or anything. So in other words, if we can transfer that to the quantum physics, measurements of physical properties such as position, momentum, spin, polarization, anything performed on entangled particles are found to be perfectly correlated, even when the particles are separated by large distance. Measurements on one particle instantly affect the entangled system as a whole. And we've seen already before that how a particle in an unknown state is changing state and it's going into this 0 or 1 perfectly aligned state of existing or not in a specific position. Measuring one particle will instantly transfer the information of choosing what will this new state be to that entangled particle in the other side of the world, which is, of course, very spooky, right? So I think that was a bit enough as a theory. First of all, by far I'm not an expert on it, and I'm not a physicist. So, yeah, if you want to ask questions about it, go easy on me, and let's see how it goes. Let's move now to Q-sharp, and let's see how all these things apply into Q-sharp. Later, we'll see a bit more details for qubits because we need to understand how we represent this massive change of informations, this information that can be represented in a block sphere in our model. So prerequisites, what do we need to have here? We need to have a 64-bit operating system because the simulator included in the quantum development kit, it follows somewhere here, requires a 64-bit operating system to run, right? We need to have Visual Studio, yeah, the latest the better, and we need to have that Microsoft Quantum Development Kit. We can download it from the marketplace by just searching for Quantum Development Kit. And I'm pretty sure if we Google it, we will also find a link for that to download it. We'll see that anyway later. So how are we going to play around with this thing? First of all, we're going to see how to install the Microsoft Quantum Development Kit, then use our Visual Studio to create a Hello Quantum world, tweak a bit things there just to understand what a qubit is, and go back to theory, unfortunately or fortunately. And then if we have time, try to create a quantum library and call it from C#. The cool thing is that C# or F# can work perfectly good with a quantum library. So that means you can create an assembly out of Q# and then use it from C#, which is cool. Not practical nowadays, but nevertheless cool. So this is where we're going to return later. I'm going to get out of the presentation right now. I will start again. And let me first share this screen and actually find the quantum development kit. I already typed it before. And quickly, this is running quantum programs into Azure, which is very interesting. Maybe we'll have a future meetup about that. And come on, it's here. Not the first one, but anyway, it's here. So we click download, we run it. I had already done that, so it's okay. We run it with our Visual Studio closed, of course, and it's done. You don't need to do anything more. Usually you will not even need to restart or anything, but it's done. So that's why I'm not actually installing it, because it's a rather easy process. I will jump in to Visual Studio directly. So Let me start Visual Studio, and yeah, it's over there already. Once we install Q# or the Quantum Development Kit, we can start a new project. Not very fast for some reason. I don't know what's happening, honestly. Anyway, we can type Q# here, and again, now it's faster. Now we see a few things here. We can start a Q# application. Q# application, this is like a command line application. We can start, these two are for Azure with provider Honeywell, or IonQ as a provider for a quantum system. And we can also start a library. We can do that later. We can call that library either from a Q# application or from a C# and F# application, and actually test it also. So let's start with the Q# application and see what's going on there. The basic one, the hello world one. And then we can make a few changes actually. Let me close a few studios that I have here because I think it's maybe too much. So give it a second. That is it. Relatively easy to understand if you're writing C# already, if you're playing around with .NET, because we have our namespace, that is it. We have our usings here. We have our entry point, that's the main. And then we have an operation, a method, let's say, which returns a unit. What is a unit? This is, we can think it as an equivalent of null, of void, sorry. This is like an operation that returns nothing and just writing this message. So if I run it, it will be just command prompt writing hello quantum world. Now, I hope that will be done soon enough. Yeah. Yeah, I honestly, sometimes, you know, how Murphy is. First of all, that's the sign of success. If you had time to check it, that's a sign of success. And this is the command line that saying hello quantum world. So, but what can we do here? First of all, one thing we can do is use a qubit, because that's not actually a quantum program without qubits. We can write, for example, use q equals to qubit. No new, no nothing here, but the syntax is quite relevant. Now, what that does actually is declaring a variable named q, an immutable one, actually, variable, of type qubit. Nothing exists here, nothing is done. We are just saying that this is a qubit. Every qubit, when we start it, is at state 0, that weird 0 that you've seen before. And we'll see later exactly what we name that, why we name that like that. It's actually the Dirac notation, but we probably see that later. So what can we do here? First of all, one thing we can do is actually monitor the internal state of the system. Now, how can we do that? We already said that, you know, we cannot monitor the internal state of a quantum system, because once we do, we will change its state. This is a simulation, right? So we can do that. It's very useful for debugging simple programs or for learning. So in a real quantum world, quantum system, this could not be done. You could not see the internal state, because if we do that, as we said, we change it. Yeah, we can do that here, which is very, very funny and useful. For that dump machine to be able to use it, we need, what am I typing here? We need the diagnostics, the quantum diagnostics, and give me a minute to type that down. So we are here. What will happen if we run that now? What? Yeah, it might think it's not. They are not 100% working correctly with Visual Studio yet, but it's going there. Let's hope it will be a bit faster than the previous. did indeed failed. What do I have wrong? I think I, of course, have that. I hope that is it. And I have another one. It's so difficult to write how I am right now. Diagnostics. Sorry for that, but I don't have my regular PC because besides my toothache, it seems nothing goes right these days, and I had to do it with a small laptop and the second screen that I have here. So yeah, but we managed it up until now, so it's okay. Now let's hope this will work. This very complicated program, it seems it does. Let's bring it out over here. And this here is the internal quantum system state. So there is only one qubit here, so we see only one qubit, and we see the possibilities of being in one state or another. Let's go through that a bit. So it's either 0 or 1 or both, somewhere in between most probably, or that qubit specifically, it's 1. This is tries to be a graphical representation, a percentage, how 0 it is and how 1 it is. We see here that it is 100% 0 and 0% 1. And actually, this is like something that we check later. It's how we represent a qubit in with the help of matrices. So this is it up until now, nothing special here. Let's just do one more thing. Let's just use, how do we change the qubit states? We cannot interact directly with the qubit, with the quantum system, and we don't do that because that would make us bind, let's say, would bind us with one quantum system like IonQ. We want to be decoupled from any quantum system. So how we change quantum states by using gates. I don't think we will have time to go through gates right now, but this, for example, it's like if you remember an inverted gate. Was it like that, the logic gate? The not, but anyway, what it does is called the Pauli gate, and it's inverting its state. So if it is 1, it will go to 0, and if it is anything in between, it will go to the opposite anything in between. And we can also have a dump pass in here. Why not? So we can see that inversion. Now notice something else. I'm actually messing around with the qubit right now using this gate, and something else will happen. This use here is actually in the earliest version, I think up until 0.11, now we are at 0.17. It was actually using, like the one that we know, and it had curly brackets to include anything that could be used in between. So when it was out of the curly bracket, like a normal using, it was discarded. Now in this version, you can just have this line, and the qubit is trying, the Q sharp will try to deallocate Q whenever it's stopped used. So it is at the end of this program. But why do we have this exception now? Whenever we stop, we don't want to use any qubit anymore. We need to reset it back to its initial state. We cannot just leave a qubit in superposition doing whatever he wants to do. We need to observe it, let's say, and then use a gate to set it up to the initial state. Now, so this, and before I close it, you see how the inverter gate, let's say the Pauli gate, changed its state, and it's now 100% 1 and 0% 0, and the same here. So let me close that. I need to reset it here, and it's done. And before we go back to check a bit more theory, let's also use the let's use the Hadamard gate. to actually see some differences here, because right now we only seen 0 or 1, and that is what we have already. Control KD doesn't work here, unfortunately, so we need to manually do that. Let's see what we'll have here now. The Hadamard gate is what we've talked about, that it's being used extensively in, did we talk about, we did, we will talk about now, sorry. It's even for me so confusing sometimes. So this is the state, the new state of our qubit. It means that it is 50% 0 and 50% 1. And this is actually the graphical representation. I don't know how helpful it is, but anyway, the graphical representation of that 50-50%, right? So let's try to go deeper into these things, but before we go deeper into these things, we need to go through some theory first. Let me reshare my screen and go back here. First of all, if you want to indeed go deeper into this, you need to remind yourself, I'm sure that at some point in university or school, you did complex arithmetic and linear algebra. It's very helpful here, and it will be nice to familiarize yourself again with that if you forgot anything. So the state of a qubit is represented actually by complex vector of size 2, the one you see there. In that thing in the middle over here, what we see is actually how A represents, let me rephrase that. In that example over there, A or alpha represents how close the qubit is to state 0, and beta represents how close the qubit is to state 1. You can also normalize that vector, of course, to this linear representation that you see below that. And in this case, and before, the A and B are known as amplitudes of state 0 and 1, respectively. Now, we have some basic states, right? We call basis states, actually, the 0 and 1. We have everything in between, but we have some basic states. These basic states, we can have, having this A and B, we can actually apply scalar multiplication and vector addition to express any qubit state just as the sum of these two basic vectors. And we see here that we end up having this. I don't try it right now, sorry, that's one step ahead. But anyway, we have this last part of the equation here, which is the two bases plus a weight. This is known as linear combination. Now, one other thing that we notice here, and I'm sorry for my mouse going back and forth. One other thing that we notice here is, sorry, this is the, let me close that. Is that these tables have two more properties in it, them, right? One is that they are normalized, and the second one that they are orthogonal. For those that don't remember, these two here actually represent the inner product of these two tables, of these two matrices, sorry. Now, this means that these two matrices here actually form an ortho vectors. Is it vectors or matrices? I'm sorry for my English, but I didn't do that. I didn't do linear algebra in English, and I'm kind of confused sometimes with the terminology. But anyway, I don't know. Let's call them vectors. It doesn't matter that much. These two, anyway, they form an orthonormal basis. This is the basis that it's also called a computational basis or a canonical basis. Now, it's not that only those two bases exist. They are also the Hadamard basis, which that's what I was about to say before, and I thought it would be late. It is widely used in quantum computer, and it's actually used in the it's called BB84 quantum key distribution protocol, which is the first quantum encryption, right? So quite a big thing, I would say. So I don't know if I should, let me see. Do I have some chat here? Alex is asking, zoom in, please. That was, I don't know. Zoom in my Visual Studio. Okay, I'm sorry I didn't see that earlier. I will do it now. Second question by Alex, but can I use a Q-sharp 64-bit? Why we need quantum computer in this case? I didn't quite understand the question. The simulator needs 64-bit, not the quantum computer. The simulator that simulates a quantum computer needs 64-bit computer. So, of course, for a quantum system, there is no 64-bit or something. I hope that is what you're asking. And Alexander says if you can use the view, you can zoom in using the view option menu in the top of your screen. Yeah, sure. I will do that, Alexander. I'm very sorry that I didn't see that earlier. I hope you can see my screen now, and I do share my screen, right? I hope everything is going well there, at least, and I will do that with Visual Studio later. I'm very, very sorry for that. We can go back again and see them very quickly. So let me give me just one more slide, and then we'll go back to code, and then we'll go back. We will also zoom in and see what we did before. So let me come here again and talk about the Dirac notation. Now, writing out each vector when doing quantum calculation takes up a lot of space, right? It's not something easy to do. And this will get even worse when we introduce quantum gates and multi-qubit systems, so like one that we have now. Dirac notation is actually a shorthand notation to help us exactly with that, solve that issue. In Dirac notation, a vector is denoted by a symbol called a ket. I think we've talked about it. We shared that again. This is a ket. For example, a qubit in state 0 is represented with this ket, and the qubit in state 1 is represented with this ket. Now there are more kets than that, right? There are far more than that. So I think I have it. Don't I have it here? Come on. Yeah, this is a ket actually, and so this thing here would be rather complex if you remember the end. Come on here. The end of our linear combination here can be very easily represented by this equation here. Now, you might not find that helpful initially, but when you start playing around with qubits a lot and with quantum programming, you will see that speeding up things makes a lot of sense. And you will also start meeting more kets than that. As we've said already in that very bad GIF before, this could be like up and down. This could be a number. This could be an irrational number. It could be anything you want. So the last thing, I think this is that I'm done with slides, so we can happily go back to where we are, and I can, of course, zoom. I'm very sorry for that. Let me know if this is okay, please, and let me go back to the chat here and see if everything is okay. Hopefully. Well, I don't see any new from the chat, so I guess you can see that pretty well right now. This is what we did before. We allocated a qubit here, and we checked the internal quantum system state. We applied the Pauli gate, which is actually an inverter, right? We check again, and then the Hadamard, and then we checked again. as we said before. Actually, this in some versions back was like that. Q equals, oops, sorry. Come on, this qubit, and you had some curly brackets here to include all of the code below, but we don't have that anymore. We have that single way of writing here, but this is actually what it does. It could be represented as this, right? So let's go back and see. I think we are okay now. I'm sorry that I had that small screen before. I think that we can actually go back and see just a bit more complicated programs, because now we sort of have an understanding. Let me run this program again and see now the internal state, because I think it would be easier for us to understand a few more things, and then go deeper a bit into writing actually a library. And I think since we don't have much time, I have one in my GitHub account actually, and I can share it with you. Is it run already? Yeah, sorry for these delays, guys. I mean, and girls. I mean, it should be much easier than that if I had my proper PC. So what is happening here? This is actually the linear representation of what we're talking before, right? These vertically are the matrices, vectors, whatever you want to call it. So this sort of makes a bit more sense now. And this is actually the radius, which one thing that we didn't see, and it might be a bit cool, I think, it will be the Bloch sphere. I think I have it somewhere, a very nice, give me a second, I will find that out. Yes, this is it. You can see here, I think, a bit better what a Bloch sphere is. This is it. This on top is state 1, or as we know that how this is represented as a cat. No, sorry, this on top is state 0. This on bottom is state 1, and everything in between is represented as a random point in the surface of this Bloch sphere, which is actually a 3D point on that surface, right? This one. I don't know, this might be helpful because you can actually start playing around with the values and understand how these interact with each other and what it means if it is here in the middle. So yeah, I honestly, I'm trying to find the balance between too much theory and writing some code. So I think we should skip that for now, although I will share the link, and whoever tries to get a bit deeper with that, what's going on now, you will really like it. So let's go back. What do we have here? We have our quantum random number. What is this doing? This is actually creating a number that it's so huge, practically impossible for or very slow for a classical computer to produce. And it's a true as it can be random number, right? So what do we have here in our solution? We see that we have our QSAR library and CSAR that is actually used to call that program, to execute the quantum random method and get the result back. If we run it fast enough, I hope, we'll see a number that it's so big, actually bigger than all the atoms in the universe. And this is theoretically a way to choose a random atom in the universe, choose it by index, of course. If that someday runs, I know this is the previous one, I thought it was fast this time. We'll see here that the atom number blah, 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 all this has been randomly selected. And how does that work? Let's first of all go back to our QSharp library. I hope you can see here. Let's see if I have any other messages. No. I hope you can see here. This has two operations in it, right? One that returns the result. We'll see what it is. That's not void. And one that returns a big int, but a big int built-in type of quantum, not a big int that you know already. What it does, this is actually how you loop things, right? This is how you are registering a variable of type, an array of result, which is mutable, and you can change it. And this here is immutable. I think if you go the mouse at some point, when it loads correctly, you should see why. Yes, this is an immutable one, and this is the biggest possible size that we can have. So what we do is that we are getting in that loop, and for its bit size, we are executing the get random request to get a result, and we are setting it up. We're adding it as an array at the end. So this is like a push in an array at the end of this array that we registered here. The sample that is created, actually, we are passing it. These two are internal methods. You can use them as is. There is a very nice guide that I will share with you later from Microsoft Docs, of course, that contains, I'm sorry, all these methods and how exactly to use them. And it's getting these bits and it's converting it to a big int, right? It's first converting this bool array, which we get as a result array, and then from that to a big int. Now, this is just a single check. You see that the only, actually, I don't know, I think I can even use that parenthesis now up until a version, I think it was 0.11. You could use the parenthesis and this was okay. Now you're getting a depreciated message that this parenthesis should not be used anymore. No idea why they were removed, because this was resembling even more to what we know. But anyway, for now, it is depreciated and we should use it like that. Same for the if here, right? Same here. You see that there are no parentheses. Yeah, from now on, don't use them. And what that does is actually creating a new qubit, applying the Hadamard gate, as we've seen before, and it's resetting only the Zen basis. Remember the Bloch sphere? It doesn't reset everything. It's just resetting the Zen basis. So it goes into that. How is that the middle of the air? God. Anyway, you remember the Bloch sphere, I guess. And then it's returning everything else. So I'm sorry, it's closing, my voice is closing slowly. So it's returning what's left, and this is converted actually into a result, right? And this result is actually what? A series of true or false, a series of bits. And this series of bits are added, and this could be 0 actually, is added to the bits array here, and at the end is created to a big int and returned only if the number created is not bigger than max. And why is that? Because we need to handle it. It could return a much bigger number, but we need to handle it from our QSharp here. And the QSharp does exactly that. It's creating a new instance of the query simulator. You will find that here, these libraries. It's a NuGet package I will show you. You can, once you have this query simulator, again using, right? Once you have this query simulator, you can get that the maximum value, how many atoms in the universe exist. Pass it on. This is actually just an example that you can also pass on arguments, right? Not only get back from the system. You can pass on this argument and the simulator, and the quantum, the generator here will use that simulator actually that you're passing in to calculate that big int that you are returning here. This is the the input, let's say. I'm sorry for this fast course at the end, but I think we are almost out of time, and I wanted to have time for questions if there are any. So yeah, I think we are mostly there. I don't know anything else to show you right now. I could share the GitHub where you can see this code run and play around with it. I could also send the blogosphere and some Microsoft Docs instructions on QSharp that you can find the documentation. And there is also a very nice thing now that I remembered. You can Google, let me open a new page and bring it over here. Quantum katas. If you type that one, you will end up in a page right here. This is training on quantum, right? There are many things to do. One of the most interesting things to do is you can either run these katas locally if you set up your environment with development kit, with quantum development kit, or you can run them online. Where was I? You can run them. I just said online, sorry. Didn't I click online? Yeah, follow the steps. Run quantum online. Yeah, sorry. Up until this binder loads, I can also show you my blog, which I also have an article. I think it describes more or less what we said already here. You can search QSharp here, and you can repeat that kind of session. This is also slow. Everything has to be slow today, and you can also write my GitHub account, and I have this program ready there. This one, George Cosmidis quantum random number. The article is here. You can find it here, but I don't know. Honestly, I don't know what's happening today. This is the quantum katas. These are two very interesting learning paths. If you go through them, then you have all necessary knowledge of complex arithmetic and linear algebra, and they are very, very useful in order to go this one to the qubit, which we more or less went right now, right? We talked about some things. After that, you can go to the gates, which this Hadamard gate and the Pauli gate, these are gates that we applied initially. And you can slowly move into superposition and learn how superposition at the end can be useful, because what we did up until now, it's only playing around with the state of a qubit, but nothing more. Some of those are extremely useful. I think there is also the teleportation, which I did once, and it was very, very interesting. And I know there are some questions. I will come back now. Quantum kit teleport. In this one. Yeah, not this one. Maybe I need Microsoft in front of it. Oh my God, this keyboard, I can't stand it, honestly. Yeah, this is a very nice and cool example. You should also go through it because I really, really enjoyed it. And it goes step by step, and you're learning actually everything that you need to learn about teleportation. So let's see the chat now. Can you please share the URL of the Blogsphere website? Yes, I can, of course, share that URL. If I can find it again, it's that one. And I can also share it here. Can I use QSharp in .NET? Well, you can create a library and consume it from a C# or F# project, but using it in production, I don't know what's the meaning yet. Maybe maybe in some experimental research project it could be cool, but yeah, honestly, you can. The short answer is you can, but there are no quantum computers out there yet. So I don't know if you have any other questions. I will also share that here too, because all these are being recorded, and yeah, it would be nice to be there for the record. So let's see here. No, that doesn't work. Why? What's going on with my blog? Anyway, it's not a topic of this meetup, but something is wrong. It will work at some point. Yeah, it works, but anyway, it's there. I think there is a link. If you go to my GitHub account and to this exam that we've seen, you can find it here. Yes, why the search is not working, I don't know, but this is actually also the article. This is more or less what we discussed already, and maybe a few things less, I don't know. Yeah, I think that was it. That's my Twitter. If you have any questions, I'm not I'm not an expert here. By all means, I'm not saying that I know these things so well or something, but it's a hobby. So if you also interested in getting into that hobby, please feel free to reach out, and maybe we can play around with Q# together. So yeah, I think that is it for now. Any more questions? So it doesn't make sense. So there is one question, sorry. So it doesn't make sense use Q# without access to quantum computer. What do you mean does make sense? It does make sense to play around with it. Since we don't have quantum computers anymore, not anymore. Since we don't have quantum computers yet, it's not something that you could soon enough go into production. So it does make sense to play around with Q# because you will learn about the future. It does make sense to be ready for it. If you like it as a hobby, you can do it. But actually, there is no production future for it yet. It might happen sooner or later, but not yet. Yeah, I can't see any reason to play around with the Q# if you want to use it for production. There is no quantum system yet. So another by Costa, can you send the link? What link? You can send the quantum services by MS as a private person free trial. Yeah, first of all, I didn't get the link. Which link do you mean? Which link of all? The quantum katas thing, or I don't know. And the second thing you're saying is that you can use quantum service, no job in Q#. There is Microsoft Quantum Research. I think you can apply for a job there if you are very good in Q#. The link you said you're gonna send. The link I said, yeah, I can share them right here, although I'm sharing in the screen. One is this, the quantum katas. That you can start playing around. This is not this one. This is the article that more or less, a few things less, describes what we have here. And this was also the GitHub that I'm sending it right now. That has this project that we've seen so far, so fast. This is the teleportation, what I was talking about. And I don't know, the blogosphere, I already sent it. This is my Twitter account. And I think I could also send the Microsoft Docs, Microsoft Q#. Although it's relatively easy to find that, but let's do that. So I think, yeah, and it's also very interesting to go through the Azure Quantum, because honestly, I'm not an expert. So I think that there is no sense for a real-life production scenario yet. Nevertheless, you can dive deeper and find out, right? I have the feeling you cannot do anything because everything that we have today are simulators. So on this, all this incredible speed of integer factorization, you just cannot have it, right? You cannot have it because there is no quantum system to do it. You can be prepared for that if you think that it will come very soon, but you cannot have it today. So yeah, I don't know. Is there anything else anyone wants? I think you got all the links for the video that I will publish to YouTube. I will try to publish the links in the comments, but you will be able to find them from what we are sharing here. And services quantum. Yes, this is the quantum services of the Azure quantum services. But again, there are some simulators, right? Like the IonQ. It doesn't mean that there is a quantum system because there is no quantum system yet. It's not ready. So there are simulators running much better and faster than the quantum simulator running locally, but that means nothing more. It's just they are just simulators. Yeah. Do you think that's it? Costa is saying it's going on quantum actually only. I'm not sure I understand. You are right. There are quantum computers right now, but they are not available for the public, let's say, and their operation cripples very fast. They are not ready to produce any non-trivial to find solutions for a non-trivial program. But you're absolutely right. There are quantum computers right now. They are just not ready to run any non-trivial programs. Yep. And Gert is saying that there are a few quantum computers you can use from Azure Quantum, but only a few qubits. And you're certain that these are actual quantum computers and not simulations, sorry? Ah, 1 month ago. Okay, if it's 1 month ago, then honestly, I didn't know. Things going much faster. So for the previous question, Alex, you might find a job with QSAP. I don't know. I didn't know that. If it's 1 month ago, I didn't know that. And only in US. Yeah, okay. You will move in US if you want to work there. I mean, I can understand that US is a bit ahead there. Yeah, most probably, even if they have a very ready quantum computer, I think they are just decrypting our messages right now, and yeah, they are not planned to give it to us all. And yes, you are right, Gert. There are different type of quantum computers. I think this is a huge topic, and if you are interested in that, and if anyone has any kind of presentation to do, or in a form of discussion or an actual presentation, then feel free to reach out. Do you think quantum computers will get to the consumers? I mean, this slide over here, this is why I put that slide. No, not that one. No, neither that one. This one. This is how we were. And now we have hundreds of times more capable processors in our cell phones. And these people had to be in that computer. And this is what we see. No, previous image. This is what we see here. Just a room with a computer. It is quantum. That was the other one was classical computer. It's a quantum computer with people in it. And at some point, we will reach where we are now. The question is, that is how interesting future can be if this is computer number 1 and this is number 2. Which one is number 3? I guess I don't think we'll find out, but I mean the future sometimes is amazing. Yeah, I didn't know that, Costa. Honestly, I didn't know that. I know about Honeywell. I know that there is a simulator in Azure, but I didn't know that there is a real one coming. So, anything else? I guess not. So I think it would be nice to end this discussion with this image. I don't know. It's kind of romantic, and yeah, it shows us the future, I think. IBM quantum devices are available to the public. Do you have a link that I can buy one? But not to the public, you mean to, I don't know. If you have a link, I would very much like that. It seems that maybe I am, my knowledge is 1 month old and many things happened. But yeah, feel free, Ryan, reach out if you have any of that very interesting stuff to share, and I would very much enjoy it. So, I think that is it. Thank you very much for this meetup, for this event. Thank you very much for joining. I really liked this interaction. You know, since it's Zoom, we could also open our microphones and have a discussion. But nevertheless, it was also very nice to do that. Muchas gracias from Romaldo. I'm very sorry that I don't know how to answer that in your native language. I would like that, but I don't know right now. Thank you all. Have a nice evening. Today here in Germany, I think many countries around, it's day off. Yeah, I know it's thank you in Spanish. I don't know how to say. I don't know how to answer to that in Spanish. Bye, guys. Talk to you until the next meetup. I hope you will have a great time. Ciao. See you.